Welcome to Module 17, Cooling Towers and Condenser-Water Optimization. In this module, we connect tower control to total plant performance. Lower condenser water temperature can reduce chiller lift, but tower fans and condenser water pumps also consume energy. The professional goal is not the lowest tower leaving water temperature by itself. The goal is the lowest total plant energy while staying inside chiller limits, tower limits, water management requirements, freeze protection, and reliable operation. The objectives are based on field decisions. You will explain tower approach, coordinate cells and fans, build a bounded condenser water reset, and avoid optimizing one component while penalizing another. You will also protect low temperature and freeze limits, consider water treatment and plume constraints, and verify performance using synchronized plant evidence. The main habit is simple. Measure the full plant boundary before calling a reset strategy successful. Avatar narration. The core concept is that condenser water optimization belongs to the entire plant. A tower-only view may reduce fan speed but increase chiller power. A chiller-only view may drive the towers to produce colder water, even when fan energy and pump energy erase the savings. The controls engineer thinks in boundaries: chiller power, chilled water pump power, condenser water pump power, tower fan power, load, wet bulb temperature, and equipment limits. The right set point is safe, stable, and defensible from total plant evidence. Tower approach is one of the most useful concepts in this module. Approach is leaving condenser water temperature minus outdoor wet bulb temperature. If wet bulb is 68 degrees and leaving condenser water is 76 degrees, approach is 8 degrees. A zero approach is not realistic in normal operation. Approach changes with tower design, airflow, water flow, heat load, fill condition, and weather. If the sequence asks for an approach the tower cannot achieve, the fans may run at full speed with no real benefit. Cooling tower staging is more than turning on a fan. The sequence may include isolation valves, bypasses, fan start, fan speed, cell equalization, and minimum flow per active cell. Water should be distributed correctly before a fan is expected to regulate temperature. Multiple fans at lower speed may be better than one fan at high speed, or the opposite may be true depending on the equipment. Confirm the strategy with manufacturer data and measured performance, and avoid frequent cell transitions that create mechanical wear and unstable conditions. Condenser water reset may be based on outdoor wet bulb plus an approach target, chiller lift, chiller efficiency, total plant power, or a combination. The reset must be bounded. Limits include chiller entering condenser water temperature, tower and basin, freeze protection, minimum fan speed or cycling rules, realistic approach limits, sensor validity, and water treatment or plume constraints. A supervisory optimizer should change set points slowly enough to observe the system response, and it should have a conservative fallback when evidence is missing. The optimization objective is commonly total plant power. That boundary includes chillers, chilled water pumps, condenser water pumps, and tower fans. Reducing tower fan speed may increase chiller power. Lowering condenser water temperature may reduce chiller power but increase fan energy. The optimum changes with load and weather. To make a defensible claim, the data must be time-aligned. Compare power, load, set point, approach, wet bulb, active cells, and operating modes over the same period. Cooling towers have limits beyond energy. Cold weather can create basin, piping, or fill freeze risk. Protection may require basin heaters, minimum water temperature, bypass or recirculation, fan lockout, cell isolation, or an approved draining strategy. Water treatment and mechanical condition matter as well. Scaling, fouling, damaged fill, blocked strainers, and poor nozzle distribution reduce performance. Controls may reveal the degradation through a higher approach at comparable load and weather, but a controls change cannot restore lost heat transfer surface. A common failure is an unattainable approach. A site may reset condenser water to wet bulb plus 3 degrees. On humid afternoons, the towers cannot achieve the request, fans remain at maximum, and the control loop accumulates error. The wrong response is to make the loop more aggressive. The professional response is to validate wet bulb, check tower performance, bound the reset by realistic approach, apply anti-wind-up, and verify total plant power. The issue is not only a tuning problem, it is a physical capability boundary. Use a structured diagnostic path before changing tower logic. First verify wet bulb and load context, then check condenser water flow and cell distribution, measure tower approach. Inspect fan and cell staging behavior, review water quality and fouling, coordinate the result with chiller operating limits. Finally, validate performance across a stable load. The evidence package should include wet bulb, condenser water temperatures, flow, pump state, fan current or speed, active cells, chiller data, plant power, and water treatment records. This checklist summarizes the field standard, validate wet bulb measurement, set approach limits from tower design, load, and measured performance, enforce chiller condenser water limits, define cell flow, valve sequencing, bypass behavior, fan staging, dead bands, and persistence. Make freeze protection higher priority than optimization. Use total plant power if you're making an energy claim. Define fallback when weather, sensor, or power data are invalid. Include mechanical condition and water quality in the diagnosis. Best practice makes optimization visible, bounded, and reversible. Operators should see the full plant boundary: chiller power, pump power, tower fan power, load, active cells, wet bulb, approach, and active limits. The sequence should show why the condenser water set point moved and which condition is limiting it. Any optimization change should have a baseline, backup, authorization, acceptance criteria, rollback plan, stabilization period, and post-change evidence. If the sequence cannot explain why the set point moved, it is not operator ready. Let us summarize. Tower approach connects leaving condenser water temperature to outdoor wet bulb. Cells, fans, pumps, bypasses, and valves must be coordinated before optimization. Condenser water reset needs achievable limits, slow movement, anti-wind-up, and fallback. Whole plant power includes chillers, chilled water pumps, condenser water pumps, and tower fans. Freeze protection, plume control, water quality, and chiller limits override efficiency commands. In the next module, we move from heat rejection to boiler and heating water plant control.